Okay, so thanks for coming. Today we have the pleasure to welcome Koki Kakiichi. He's visiting the lab just today. So Koki is going to give, did his PhD in Japan?
No.
Where?
No, MBA.
Ah, yeah. You did your PhD at MBA. Then you moved to UCA, right?
Yeah.
For a postdoc. Then Santa Barbara.
Yeah.
For a postdoc. And now you are an assistant professor?
Yeah.
Okay, at the Cosmic Dawn Center in Copenhagen. And you're going to talk about a journey to the universe in 3D, quest to distant galaxies, black holes, and reionization.
Okay, so thank you very much for coming. So my name is Koki. Thank you for setting up this seminar. So today I just want to talk about our journey, including people all from London, kind of fast lighter, right, to the universe in kind of 3D. So of course, the kind of main question we are after is what happened in the first billion years of the universe. By now, without actually looking at the picture thing, right? We can imagine what I want to show here, right? But to actually say kind of state of knowledge, I think more blank screen is more like what it is than kind of cartoon. So of course, with the simulations, we can of course, as we know, imagine what would happen, right? As the universe grows, dark matter coagulate and the fast star form and galaxy form in the last day structure of the universe. And then, of course, there's a lot of radiation coming out from these galaxies, and then they transform the entire environment universe from fully neutral phase to the fully ionized plasma that essentially surrounds us today. That's, of course, as we know, the process called cosmic reionization. And along the way, as star dies, and then as a supernovae, they enrich the surrounding with diverse chemical elements. And then, we can see enrichment of the entire universe. But of course, the challenge here is to really make sense of all this, kind of test this picture based on kind of 25% of the visible matter we see in the universe. Right? That's a huge challenge. Of course, with the power of James Webb, we can do this now. So, as a person, who started PhD as a purely as a theorist before Richard sort of convinced me to work on the observations, right? It's really amazing that the kind of huge progress people made, including Harry Katz and then people from the Thiessen like Enrico Gaudi and the collaborators to really simulate the entire the first billion years of the universe in the computer, so we can really simulate, based on proper law of physics, what really happened, how the galaxy will look like, what the structure of the galaxy that we are as the universe, and that looked really, of course, really realistic. And then, of course, the simulations always balance between the resolutions and the box size, and then Thiessen people, for example, push more limit to the large box to really capture the formation of the galaxies in the context of the large scale structure of the universe and the realizations, right? So with this, as we know, the Webb was of course revolutionary, and we by now have the position to test for the picture we really imagined. Yeah, of course, the power of the Webb is really the spectra. We actually know, seen this many times. But I think still remind, kind of rather fantastic to remind ourselves that the power of the instrument to really get all the nebula lines to really dissect the physics. So now, right, it was only few in the first few weeks or months, but now we have so many of them on the back shelf, kind of a shelf on the computer.
Thank you.
As you go, we can really take a look at the spectra of kind of thousands of galaxies, rather interactively. So that's, I think, a huge step forward. So now we have easily over 100,000 James Webb spectra beyond redshift 5. So this is a plot from the Guido. It's kind of compiling like near spec prism spectra of around 500 galaxies. And then, on the right, I'm showing the compilation, like a effort done by Roman, showing like a more than 100 strictly spectra, right? So we are really at the position to really understand what's going on in the early universe with the radio spectra, right? So now, we are really solved for, or physics of the, we imagine what's happened in this picture. We essentially saw hundreds of times how the early galaxy form and black hole, early black hole form, what drive ionizations, and what the history and the morphology of ionization. That's of course the question we are always after. So before I go into the more topic of ionization, which much closer to my heart, I just want to highlight some of the few kind of exciting things that I find personally. Of course, that this James 11, that's the most luminous, but not most one. That's just 10 luminous galaxies. Reveal like so many emission lines, from which we can really understand the physics of earliest galaxy formations, right? And then with a search of very faint object, and then with the spectra, we have some hint towards a kind of finding the fast stars, right? So this is the case. This is an example from the discovery of the extremely low energy system by the Vanzella. So I just want to say this is a really exciting thing. Of course, another key important issue or topic is the kind of emergence, like another overabundance of like faint AGN or supermassive black holes. So with the Webb, as we know, that we find a more abundant low mass AGN than more than expected, which is sometimes known as the little red dots. Given the kind of abundance, of these early supermassive black holes, and kind of put us challenge on how they really form, right? Given that there's so many of them and they actually form very early time, there's debate whether they'll actually need kind of formation mechanism like super identity accretion onto the black hole, or like the massive C that really coming from direct collapse or the black hole, like of the early system. So now I want to move on to more on the reionization. So before the Webb, the state of our knowledge was a lot scarce, right? Of course, we knew that luminosity density of the galaxies, and then we had to extrapolate the below our detection limit, and then of course now beyond the ship 10. And of course, we didn't know nothing or little about the state fraction of the ionizing photon. We kind of assumed that the state, ionizing photon from the galaxy to the entire IGN would be roughly like 10 to 20%. Also, the production, how much photon actually produced inside the galaxy, we didn't know the number that well. We had to assume that's rather like this number. That's essentially assuming like a standard set of populations, right? But then with the Webb, of course, we can actually witness the sources of the ionization, right? So here is the work by the APEC 2024 that we are looking with the power of the gravitational lens. We can really see the kind of very faint system that we think it's really the major driver of the ionization. So one of the surprising things was that at least in this object, the production of ionizing photon in these galaxies was a lot higher than what we expected. So in a sense that we might need like young, metal poor population to let this happen. But if that's the case, we may not need the large escape fraction that we have thought that was needed. So that's like, of course, knowing the escape RZ photon production is one side of the story. The escape fraction is really the key parameter we had actually no idea about at the epoch realizations. But with a spectra and with a calculation that can be done at the low-Z system, also with the help of simulations, we actually have a hint of the high escape fractions beyond redshift 6. So this is the plot from the Jade with Ayush Saxena, who couldn't make it here today, unfortunately. But that's actually exciting because we can have really a way to test the parameter that was really needed, or like blocking us to make it understand what's going on, what really drives the realization. So we have observational way to infer whether that picture we thought was there is really true. So with all this, right, with the possible elevated production rate of rising photon Xi ion, and with a high escape fraction, there's a debate whether now we have way too much photon than we expected. Like if we actually believe it's high production rate on its photon and combined with the high scale fractions, we might have too much photon that drive ionization too early. Because Sally's shaking the hand. That's true. Yeah? But of course, that's like to food of thought to think about. Okay, kind of a puzzle that we may face. But of course, after all, why do we care about the escape fraction and or Xi ion, right? If you care about ionization, of course, that's an important number. But if you care about galaxies, I mean, that's just a number. It doesn't matter, right? But of course, I argue that's important because that really, has implication on the physics of the, ionization error galaxies. Here it's kind of on the left, I'm showing the plot of the escape as a function of the Xi ion. So the red is what we sort of require to drive ionization. So essentially product of 25.5 or 24.4 in the product like this. And with the measure of the Xi ion, which is on the blue, right? So with the two constraints, we can sort of start breaking degeneracy and then, set number on the what's value of escape on Xi ion. So reason why I think is important is that, if we have high escape fractions and the real modest or low Xi ion, that means that, the picture we thought is kind of true from the simulations, right? We have a hole in ISM and our photon escape through this hole. In a sense that we actually need like rather large feedback and then possibly turbulent cloud to get this punch the hole through the ISM, right? So this is the kind of picture that we have in our mind, and then this is kind of simulations in this model. But if we have like a very extremely high Xi ion, a low escape fraction, like as low as possibly we could get in the Milky Way or large Magellanic Cloud, we may not even need to punch the hole through the ISM. We just need to forcibly ionize everything on the way, and then what's left behind will just escape to the IgM to redrive the ionization. So in a case, in this kind of extreme picture, structure of the ISM may not be look much different in the highest galaxies, but rather the property of the star itself could be very different in the early universe. So because of these reasons, I think it's still important to understand and kind of measure these properties as accurate or as possible. So regarding to the AGN, as I said, and as usual, finds, right? We have more abundant and faint AGN than more than we expected. But given that these systems are rather like known to be obscure, so their actually contribution 2D reionization could be rather minor, but it could be less than 25% or less. So of course, it does not mean that we may just disregard Asian contribution completely. Still, like I think it's the possibility of like Asian assisted reionization may happen, but definitely not the Asian dominated reionization. So let's just move on with more on the reionization. So if you look at the spectra of this 1,000 or 100 galaxies that we have with the Webb, so on the y-axis, I'm plotting the equivalent widths, like lambda alpha decrement in these galaxies. So the red means that the lambda alpha is completely absorbed and diminished. On the blue, it means the lambda alpha in emissions. So on other edge, if you go higher and higher redshift, our photon more preferentially start eating away in more distant universe. So that is, I think, clear indication that as we go more than redshift 7, the universe is really getting more neutral. So this is really, I think, the frontier that we can first time reach with the Webb, because before, because this effort to lambda alpha, has been done before the Webb, that has been limited by redshift 7 or 8. But now we can go rather easily beyond redshift 8. So this is, I think, the really frontier of the application of lambda alpha visibility on the SMBH reionization. But of course, there's a debate whether this absorption is really coming from the IGM, meaning that's really due to realizations, or possibly kind of changing in the system in the galaxy itself, like dump lambda alpha system, possibly other means. So interpretation is still like on the way, but we still have but we still have information that's needed to really drive the reliability constraint. That's, I think, really important to know. Of course, on the other edge, as I said, the galaxy has less and less lambda alpha, but there is some system that we can clearly see lambda alpha in emission beyond redshift 8. So just to highlight the case, right? So even in redshift 11, redshift 10, we see if you look at the system with in higher spectral resolutions, we see the lambda alpha. So that's really hinting the existence of an ionized bubble. Regional IgM where the lambda alpha photon can freely escape to reach to us. So that's really the hint for the patch reionization and the morphology realizations, right? So now that with the Webb and lambda alpha study, we can really start inferring the kind of morphology realization. Before the Webb, our knowledge was more rather just a single number. What's the neutral fraction of the universe at given redshift. Now we can start understanding what's the bubble size and their structures, right? So that has a implication on the sources that drive realizations. So now that so Webb is really pushing the frontier of distant galaxy realization. But so far, essentially, we're asking everything for the galaxies. We have wonderful map of galaxies, but then we try to infer everything just by looking at the galaxies, right? And the kind of question that I sometimes ask myself is like, kind of case for astrophysics, right? When do we stop? Like, at which point we think we actually solved the realization? So in my opinion, right, maybe if we could sort of visualize all the gas in the universe, right, including IgM, that's where, in my opinion, realization happens. If you could do this, and then now we can sort of see, okay, this galaxy is contributing to this bubble, this is not doing this, then maybe we can sort of say that kind of solve the realization maybe. So that, of course, that having this handle on IgM and galaxy is really important to really understand what drives the realization. So this is a project where we really started in London in the first slide. So as we know, alpha forest is the really cleanest probe of the IGM. Of course, the idea is that as the light travels through the universe, absorption lines in the background quasar or background galaxies even imprint the structure of densities and the background temperature of the IGM. So because this is really clean physics, right? We can write down the equations and we can really measure these properties. So we can really understand what's happening directly on the IGM with alpha forest. So of course, that was only half the story. Now that to understand what galaxy did to this IGM, we need to make a map of the galaxy in the volume we have measured of the alpha forest. So essentially, by spatially correlating the galaxies on the transmission property along the alpha forest on the side, I argue we can exactly test what really drive the universe. So this is really the effort that we push forward with Roman and Richard and with the help of Nicola and Sarah, of course, with the grant with the Keck and Mies now being applied widely with the James Webb, including Eiger and Aspire that I'm going to talk about in a minute. So this is kind of a concept that we did, right? So this is a picture from I think
a long time
long time ago.
Not that long.
At the time, I was like a theorist. I tried to do some forecasts and to propose it together to go to telescope. So this is from the first round we did with I think Nicola and Richard. So they're kind of happy because it can extend first time in the telescope. Right, that's cool. Of course, there's a huge bump. This journey was not quite there. So I just want to keep it secret here. So one of my first attempt, we had an issue with a slit mask. So what happened was like, this is actually the first one we did with the Roman. And we saw, after afternoon calibrations, there's something wrong. We had a pitch black picture on the image. We was wondering why. But then it happened that one of the slit masks, right, like metal plate with a slit, there's no slit in it. Essentially, we just insert the complete metal plate in front of the camera, right? I mean, in a sense, we try to do slitless spectroscopy. We want, because Roman was, meant to do the Barclay's James Webb. So even better because it can. Anyway, so that was quite an issue. Of course, we learned quite a lot, and we managed to do that some of the data this time, like that's just a story I wanted to share for fun. Of course, we charged onward, and this is kind of past result, kind of a long time ago now, but like I just want to show you the observational map of the cross correlation between our forest and the distribution of the galaxies, and we have a hint of this, this kind of cross correlation between galaxy and the more transmissivity of the IGM, right? But this was only one. With the Mies and the Keck, we really tried to expand the sample. But then it was at this point it was really clear that to actually measure this, we need to really overcome the cosmic variance. You can clearly see that the diverse transmission in different line of sight and the different number density of the galaxy we have in each sight line, right? So to really get to this measurement sorted, we really need to assemble so many quasar sight lines. So we, of course, with this past Mies plus Keck attempt, we managed to measure the cross correlations. And with this measurement, we try to derive the escape fraction of the galaxies at redshift 6. So I think Roman gonna talk maybe a bit on this one, so I'm gonna put this also in detail. But like a kind of conclusion was that we thought the faint galaxies should release enough atoms radiation to drive the reionization IGM with a escape fraction 10% or so. But of course, it was difficult from ground But now with a true slit spectra, right, from the Webb, from space, we can easily get hundreds of spectra with a or three-dimensional design. So this is a program for Aspire, led by Figure One, now in Michigan. So this is 65 Cycle-1 program to really assemble the 25 quasar fields in a galaxy survey in the 25 quasar field. So here is a compilation of the all three emitters we have from this field. So we really have like nearly 500 all three emitters from redshift 5 to 7 around 25 quasar sidelines. So now that we can really cross-correlate property of all these galaxies with the property of Raman forest to really pin down what really drive the reionization. Here's kind of fast view on this effort to measure the galaxy IgM cross correlations. Here I'm showing the Raman forest transmission in the left y-axis, e to minus tau, and then distribution of the all three emitters in the exactly same sight lines. I just want to highlight some of the few regions. So here we can see that there's more galaxies and there's more transmission of the IgM. That's indicative of that of the fact that like this all three emitters is really resulting highly ionized environment of IgM at redshift 6, right? So of course we can do more quantitative. So this is work by the Zhang Yu Lin in Arizona. So when she measured the effective optic depths in each sight line and then along the location of galaxies, she clearly find the more transmissive IgM compared to the mean. So that's again more quantitatively supporting the argument that IgM around these all three emitting galaxies are indeed more ionized than average. So we can move on, like we can keep going on this effort of cross correlations. Here I'm correlating the location of galaxies with each Raman forest transmission pixels. So what I'm doing, just go back a little bit. Right, here's galaxies, and then simply measuring how much the degree of the IgM transmission as a function of distance from the galaxies. So the black is our measurement. So it goes like 0 to the positive around 30 million parsec around galaxies. And red is around shuffle. That's like in a case when there's no correlation in these two. So now that we can clearly see there's something in it, right? It's, without having like line to guide your eye, there's certainly, I would say there's certainly signal that goes up and down. So physically, we think this is happening because the effect of ionizations around these all three emitters. On the right, I'm showing kind of cartoon illustration of this picture. So on a large scale, because IgM is more ionized around galaxies, we should see more, transmissive IgM, right? So the signal should go up. But if you go really too close to the galaxies, because this galaxy is residing in the dark matter halo, a more dense region, because optical depth is simply proportional, like to the density times the interfraction of IgM. If you go more dense region, things get more opaque, so the signal goes down. Okay, so this kind of rather characteristic shape is what we are seeing in this observation with the Webb. So it's really, I will argue, we have evidence of the large-scale excess IgM transmission around redshift 5.8 galaxies. So now to really make sense of what's going on, right? So now we can compare this measurement from the Webb in the context of full cosmological radiation hydro simulations. So that's kind of dream that, kind of cool because we have Webb and then we have simulation on the other hand, and we can really make sense of the two. I think that's something that really I like as a methodology. So this is the picture from these simulations that I'm using to compare the observation with. So now here's comparison. So the black is a measurement, and then all the color lines are the kind of prediction from hidden simulation. think the match is, pretty good. I think especially given that the simulation was run before we have data, right? So it's really kind of going in the direction that we have, right picture of the realization. But if you look at, underlying map that explain these observations, we actually need things like this neutral island, still the existence of this regional IGM that's still not yet realized, right? So we think because of this, we have this large scale hump in the transmission of IGM. Of course, this is still like not 100% sure. But we argue that this observed cross correlation really favored, rate reionization, and then the reionization process is ongoing, and then these galaxies had to be kind of surrounded or like hosted by an ionized bubble for like 40 megaparsec or so. Of course, to make this bubble, contribution from all 3 emitters is definitely not enough. This is the all 3 emitter in the simulations, and you see like many galaxies that really collectively driving the ionization, right? To make these things more, this can versus evolutions, just like saying that and vertically consistent. So to really understand, right? So to really check whether all 3 emitter, what's the contribution of 3 emitter versus the training population we have not seen yet. Now, because we can measure or infer the IGM, UV background in the region from the lava forest transmission spike, we can exactly gauge the contribution of the galaxy we see to the reionization of the IGM. So then, if you assume like 10% sphere fraction or 3 emitters and standard star iron, this contribution from all 3 emitters we see is much less than 1%. So definitely the galaxy we see as all 3 emitters is really not enough to drive reionization, at least in this region. Of course, we can be more drastic assumption. We can assume all 3 emitter could be just spent AGN, because we only have information of the all 3. We don't know that's like AGN or not. But even if you assume that's the case, like 100% sphere fraction from AGN, the contribution is certainly much less than 7%. I think it does really indicate that like faint galaxies are really the main driver for the reionization, at least when you complete the reionization. So I just wanted to, to actually see the more faint unseen stuff, the actual absorption line really helps quite a lot, because absorption line, in the spectra of the quasar, like meta absorbers, because these are we think the star system that is around the galaxy, but yet still below detection limit. So this is again kind of going back to our earlier work. In this region in particular, there's actually abundant O3, so O1 absorbing system that's feeding the faint system inside the bubble, like below detection limit. All right. Let me just before we move on, I just want to highlight kind of interesting things I thought about from the observers. I mean, so with the observers, right? Because we have access to the stuff that we simply cannot see even with the James Webb, because any telescope detection, flux limited. But with the observer, we have access to the system that simply cannot be seen by light. But some of the system, there could be the enrichment pattern in the IGM that could hint the enrichment from the boosters, right? Of course, that's still like debated. But if you can measure, in addition to this IGM galaxy cross correlation, we can measure the observer galaxy cross correlation. We have a way to measure the dark matter halo mass for the faint galaxies, and then understand what's going on in the system, even below the direction we cannot even see with the web. Okay, let's just go to a different topic. So now that what did AGN or supermassive black hole did do in terms of ionization, right? Or like how did they form? So in the sightline, there are sometimes systems that actually show a hint of the AGN activities. So this is just one case that I just want to highlight when kind of going back. So there's actually have a system that has a nitrogen 5 in the sightline of quasar. So with this, we could, in principle, measure the contribution of AGN into the realizations. So, but then, like, you know, interesting. All right. So I think, of course, we can think about what the drive ionization. But I think more interesting thing would be that, you know, we can convert the effect of AGN ionization to the IgM back to the hardy supermassive black hole glow, because, you know, your speed of light is finite, so distance from the galaxy AGN to the IgM is some distance. Your speed is finite. There's a time that requires for the photon to travel from the AGM to IgM. So that actually implicates the previous activity of the quasars in the reionization state of IgM. So if you can measure the IgM transmission as a function of distance from the AGM, we can recover how the quasar light curve, hence that because the quasar luminosity is tied to the hardy black hole glow, we can infer the hardy black hole mass assembly occurred at the cosmic time. And so we tried to do this with Sarah back in 2020. So here's the kind of one case that we actually saw from observations that along the transmission of the background galaxies and Lam alpha emission features in the galaxies. So here, just quickly, just show like saying, I want to say that you know, by looking at the transmissive Lam alpha, transmission of visibility of Lam alpha, we can at least infer how this black hole might have grown, like quasar that will happen in past. So I think that's kind of cool because by looking at this past impact of the quasar activities in IgM, we can infer how the black hole might have grown. So here's a constraint from this kind of concept called quasar-like echo, and then orange is the measurement from the quasar galaxy cross variations. So if you kind of combine these measurements with, you know, it seems like there's not enough time for the quasar to go, meaning that, you know, because as we think how the way we think how black hole grow is through the quasar activity, because that's how we think it's grown. But given that we don't have enough, you know, quasar may not have enough, black hole may not have enough time to gain its mass through the quasar activity, it actually hints that we actually need the gas upscale phase growth of the supermassive black hole, or possibly the super Eddington phase into the super Eddington accretion phase to explain the population and early black holes. Okay, to finish up, I just wanted to introduce the Cosmos 3D. So what is Cosmos 3D? So Cosmos 3D is a large Cycle-3 public treasury program with a 265-hour of James Webb time to really carry out James Webb near-Earth wide field grism spectroscopic survey of the Cosmos Webb field. So that's the largest contiguous spectroscopic survey we have done so far with a Webb. So of course that science driver is coming from this three pillar, the early galaxies, and in the context of large scale structures, and how this supermassive black hole growth and the nature of little red dots and reionization of cosmic web. So really the kind of overarching goal is to get the mapping of all the structure in the universe in 3D from the dawn of galaxies to the present. So in terms of the more specific setup, we are using near kind of 444W grid spectroscopy to cover system between lecture 0 to 9 with over 1,000 square arc minutes with a parallel MIDI imaging to capture dust emission from the AGN and the dusty system. And then what also I find it more exciting these days is the kind of possible extension to the time domain in the one micron. So that I think is really important to really, pin down how the black hole grows as through the variation variability, also to capture the faster tangent. So of course, this is built on the legacy of the Fresco and the 3D HST, and of course, many years of community effort that put in the Cosmos, right? Of course, including Cosmos Web, and all the way up to the initial creation of like HST program. So now that what we started is this picture, and then it's I think it's quite a journey. I find personally. So we had a meeting in this Cosmos meeting to really talk about what we're gonna do, all this stuff with different people. So here's collaborations. Right, so of course there's a huge heavy lifting is done with my co-PIs, Figure 1, and other people. And then of course this program is absolutely impossible with the help of many people in this list. I just want to highlight the work and let's acknowledge the people who really done the heavy lifting in the first week of the data acquisition. Roman, of course, and then Gabe and Zihao Lee, Brian, and Fega and Zinyi. So we actually got the first data actually 2 weeks ago. So here is the gradient image that we get from this program. And then see, I just wanted to really highlight the effort that put in by the PhD student from Zihao Lee. So in this even single kind of exposure, we do have the system of those 3 meters at redshift 7. Right, so that's of course that's preliminary. I just wanted to show case that kind of fast data is really arriving. The main chunk of data will arrive next April and May. So with this, we try to get like the understanding of these 3 physics, how the fast galaxy form. Like we really want to measure the clustering of these luminous galaxies because so far we have information from the spectra, but we don't know how the underlying dark matter structure in the universe. Only with the clustering we can connect these property galaxies into the underlying dark matter halo properties. So we can then argue, understand, whether we actually have missing physics on the massive galaxies or maybe passing cosmology. Of course, we love that, but we want to test it. And of course, same thing for black hole. With a clustering of red dots or like supermassive black hole, we can connect the formation of supermassive black hole in the context of the mass assembly of dark matter. That's, I think, the next key step forward in solving for the mystery of red dots and the formation of early low mass or faint supermassive black hole. And then kind of one thing that I kind of want to talk a little bit in the last few minutes is the possibility of mapping the IGM, the reionization, through the IGM tomography from this program. Now, of course, the really powerful Cosmos is really how we have fantastic instrument like the Euclid and the Subaru HSM PFS to really, put these James Webb observation in the context of multi-wavelengths, multi-effort from many different telescopes. And then, something that I'm kind of more personally excited about, the extension of this time domain science, the way to actually capture the fast light from the deep infrared transient sky. So that's something I haven't really appreciated initially. But if you think, because things, if you want to capture the faint transient object, only way to do this is to get a bigger telescope, right? So if you want to go deep imaging, in principle, we can spend like years on single telescope and just capture that in principle. But to capture the light in a single frame of time, I think the Webb is fantastic to do this. And then not only with this, I think I argue we can really go for, searching for like fast stars and black holes. I think that's something extremely exciting about. To finish up, so I just want to show you a bit of technique that I'm kind of excited about. So the IGM tomography has been the extremely successful redshift 2 to 3 using a ground-based instrument. But if you want to do this at beyond redshift 3 and to really go to reionization epoch, we need an extremely large telescope. So of course we don't have that at the moment yet. But way around is that we can use, instead of doing spectroscopy, right, to capture the faint alpha transmission around background galaxy, we can instead use extremely deep narrowband imaging. So here is a cartoon illustration of this technique. So along these background galaxies, we can have a narrowband filter that capture exactly the alpha transmission along this system. So we combine with all this broadband imaging we have from different instruments, including Webb 2. And then essentially, if you have a more SCD fitting, measure of the alpha transmission from narrowband filter, we can actually do the photometric measurement of the IGM transmission along like 100 galaxies in this single field of view. So with this technique, we can really, I would argue, we can really reveal the large scale map of the galaxies and the IGM all together. So this is the kind of pilot study we did with the Subaru data. So on the color map, I'm showing the IGM transmissions as a function of space, and all these points are the Raman alpha emitters at exactly the same redshift slot. So we can now really see that how the galaxy distribute in relation to the IGM. So maybe that if you have more transmissive region, we actually can identify exactly the location of Arnold's bubble. The location of protocluster may appear as a more opaque region IGM, and so on. So at the moment, we have no detection from this, to measure cross correlations. I would say that's rather still consistent with with the evidence of rapid evolution of this cross correlation at the end of reionization. So to finish up, I think the real power of the cosmos of Webb is not only with the Webb, but we kind of combining all the possible instruments we have on space and the ground, right? So in a sense that this tomography is only possible by combining all these three to make things that happen that we thought it's only possible with an extremely large telescope. So with this, I argue we could really reveal the IGM structure of the IGM and distribution galaxy all together to really, in a sense that they kind of dream of galaxy across the SKA 21 centimeter cosmology come true. The 21 centimeter cosmology designed to map the IGM in epoch realizations, but we don't have that yet. But with this one, we can actually start in doing science that we thought not possible with the SKA or ELT. I think that's exciting. Of course, even with the ELT era, given the field of view of the mosaic is rather small, I would say it's extremely useful to have actually map, large-scale map of the universe. Only with this, we can actually navigate, okay, where you want to point the sky, you want to look at more candidate region of Arnold's bubble or pyramid or protocluster. So only with this, I think we can really capture the full 3D view of the universe. So I just end here with a summary. Okay, so thank you very much.
Do you have any questions? There we go.